Oh, I was just looking at the chat. And Becca, if you want to monitor the chat for me, that would be great too.
Okay, I will monitor the chat, and also just so you guys know, this meeting is being recorded, and we'll post it in the wood utilization space. I don't have any plans to post it anywhere else, but if you guys, change your minds, want me to put it elsewhere, we can do that. So
Awesome. Awesome. Okay, so I will go around and I'm just going to say hi. I think you all know me. Most of you do. My name is Ann Matek, and I am co-chair of the Wood Utilization Community Practice, which is sponsored by the Fire National Network, the Fire Adapted Communities Learning Network. Also the coordinator of GFFP, the Greater Flagstaff Forest Partnership. And Becca, why don't you go?
hi all, I think we've all met at some point. I'm Becca Samolsky. I'm the director of Fire Adapted Colorado, and I've been working with Ann on trying to keep the wood utilization topic highlighted among fire adapted communities practitioners for these last, I don't know, Ann, 4 or 5 years, four at least.
Yeah.
So I'm really excited to keep those conversations going and have some folks joining who really have the wood utilization background as well, so we can continue to kind of bring some of the folks on the ground who are trying to do forest thinning together with folks who really have the experience and the knowledge to help figure out what to do with all that wood. So thank you guys for being here today.
Awesome. And Annie?
My name is Annie Lutz, and I actually work for a private consulting firm, SWCA Environmental Consultants here in Flagstaff. Archaeologist by trade, but fire ecology and forest restoration is my jam. Former wildland firefighter. And actually, with the last presentation with the cross-laminated timber, I've been fascinated by it. I'm so interested in it, and I've been reading all I can about it. I'm just like, whoa, like,
Yeah.
who would have thought? I'm literally, like, maybe it's my background being the daughter of my dad was the Habitat for Humanity construction manager for Northern Michigan for a long time, but I'm fascinated by it. So I'm getting more into understanding the end product and how it fits within our challenges that we have with, initiating our forest restoration treatments like forestry, and how it's not just one factor. So I'm excited to be here. And yeah, and Chris, I really enjoyed the Town of Payson code presentation that you did. So
thank you so much for participating. Great.
Yeah,
I'm going to get that recording loaded up today, so it's ready.
It was great. It was really, really interesting. It was really exciting to see that come to fruition. So
it's been 20 years in the making, so yes.
Yeah, and Chris, I wanted to just give a mention that when the time changes to November 1st, your webinars are going to cross over to this COP. So just a FYI, because we'll be going in Arizona from 10:30 to 11:30.
Yeah, I may not be able to participate at that day.
Yeah. And Chris, why don't you introduce yourself, please?
Okay, my name is Chris Jones. I'm with the University of Arizona Cooperative Extension. I'm an agent in Gila County. This is looking down at the county off the rim. So that's a nice background shot there, a place called Promontory Peak. I partner with Ann on the Arizona Fire Adapted Community Steering Committee, and we've been doing projects with that. With COVID, I started doing a weekly webinar series I'm calling Garden and Country. I try to keep my horticulture and gardener people happy, but really been using this opportunity to network and educate about some of the wildfire issues we've got going on. Another thing I want to mention is I've got a group called the Cobra Valley Watershed Partnership. We've been looking at water issues, but this year we decided healthy forest, healthy watershed would be a good topic, even though we're down the desert scrub here in Chaparral. And it's going to be an opportunity to really start to engage on wildland urban interface issues in the community that we've been able to kind of looked to the side because they weren't happening. You know how it is down in these communities. And with the way red brome took off in Arizona and heading south, I don't think we could do that anymore. So been making some really good contacts using that as a tool, and just going to keep on moving with it. So that's just a few things going on me right now, and I'll just pass it on to whoever's next. Thanks, Ann.
Yeah. And Jay.
Morning, Jay Smith. I'm the Forest Restoration Director for Coconino County. Got 20 plus years experience in the wood industry, logging and sawmills in the Southeast, and a little bit of logging here in Arizona. I think our biggest project right now is we're getting ready to start back up on Bill Williams Mountain, helicopter logging to try to finish that first 300 acres. And we're hoping to put another 200 to 300 acres out to bid this year for probably logging next year. We were looking at trying to get some slopes that might be more adaptable to Ponce type tethered logging versus the helicopter logging, but you know, we'll let contractors tell us what they need to do on the land that we've chosen. So yeah, we're really just looking forward to trying to continue to, we got disappointed with the RFP of the Forest Service getting pushed back potentially to as late as March 2021, as far as them choosing a contractor or contractors. So, you know, we're still pushing for industry in Northern Arizona to help us with biomass, with just wood utilization. I know Senator Sally just put in a bill for biomass utilization that she hopes would help in Arizona. So we'll see as, you know, we start getting politicians involved as well. So
Yeah, maybe if we have time, we can expand on that, what Senator McSally is proposing at the end.
Or if you have a link to what's being proposed too, please drop
We
that in
do.
the chat. I'd love to take a look and pass
okay,
it along.
yeah, I've got, I should be able to get that link.
Yeah, we did that yesterday at Forefry. That's awesome. And then we have Burgeon. I'm not sure who that is. With if you could introduce yourself. You might be on mute. Okay, we will see if they can tune in. But if you are able to introduce yourself, awesome. And if you just need to, and if you can't, that's okay too. So we're gonna have this presentation from Damon, and we're super excited because Damon just joined ERI and did his, this is your doctorate work, Damon?
Yeah, that's correct.
Okay, so we're really happy to have Damon today to talk about this because really figuring out what to do with low value ponderosa pine is a key, I think, to solving our wood utilization dilemma, especially here in Arizona and Southern Colorado. So Damon, I'm going to hand it over to you. And if you want to share your screen, feel free. And we're looking forward to this.
Yeah, thank you, Ann. I'll pull up my title slide here. All right, can everybody see that?
Yes.
Okay. And can you all hear me okay? I've had some problems with my mic.
Yeah, I can at least. Everybody
Okay,
good with
great.
that?
Well, I think I know, have had the chance to at least virtually meet most people in this call, but for those that I haven't met, I'm Damon Vaughan, and as Ann mentioned, I'm a new employee at the ERI. I work in the Forest Operations and Biomass Utilization Program that Dr. Hans Hahn is heading up. And prior to that, I was a PhD student in at the School of Forestry here in Northern Arizona University, and I'm going to talk today about my dissertation work, which, as you can see, is on the wood properties of ponderosa pine in the Southwest. And this will be about a half-hour presentation, and we have a small group today, so we'll hopefully be able to have some good time for discussion afterward. And I will just get started with this. So most of us on this call are Northern Arizona people, or at least in the area. And so it's not too, unfortunately, it's not too uncommon to see headlines such as this one highlighting the difficulties that the projects like the forestry have faced in implementation over the last 10 years or so. And so for those that aren't familiar with the area, I think we all are, but the dominant tree species is ponderosa pine that's being removed. And a lot of the challenges come from the enormous cost of doing these treatments relative to the low value of the material being removed. And so I included this quote from a local logger that came from this article because I like the quote because it frames it in the context of a wood quality problem. And there are a tremendous number of issues in addition to wood quality, but I'll be focusing on this wood quality piece. And the idea is that what we produce from the wood is really limited by the properties of the wood and the quality of the wood. And most of it that's being utilized at all currently goes to the production of pallets, which are a really low value product, or bioenergy. And the idea is if we could learn more about the properties of the wood, we might be able to direct at least some of it towards higher value products like lumber, or engineered products like cross-laminated timbers. And so that's kind of where my project came in. And the idea was to quantify wood quality and variations in wood quality, and from that we can learn what we can be making out of it to help offset those treatment costs. And so wood density is the best indicator of wood quality. And by wood density, I just mean the bulk density of the material, the weight for a given volume. And to illustrate that, I've got this simple image here of pine, which tends to be lower density than oak. And you can see the pine floating a little bit in water, whereas the oak sinks. Wood density is a really important structural parameter, and it correlates really strongly with most other wood properties. And so to go a little bit deeper to a cellular level, the cell wall material of essentially all species throughout the world of trees is essentially constant at about 1,500 kilograms per cubic meter. But what leads to variation in wood density is the variation in the size of the cells. And so you can see in this blown up wood block here, the early wood cells are larger diameter lumens, which is the conduit for water transport, whereas the late wood has smaller diameter lumens, and it provides more mechanical support for especially large trees that need that mechanical support. And so higher density wood is typically considered higher quality, and higher value products can be produced from it, such as lumber for building houses or engineered wood products. But that's not to say that we can't produce high value products from low density wood. There's some products like oriented strand board or biochar where lower density wood actually confers some advantages. So another useful metric to quantify wood quality is with stiffness. And what I mean by that is just the amount to which a piece of wood resists bending. So you can see in this image here, I've got two identically cut pieces of wood, and I've hung a weight from one of them. And you can imagine that if I release that weight, it would spring back to its initial position. And that's because wood, throughout most of its range in bending, is an elastic material. And so the force with which it returns to that original position, that it resists bending, is the wood stiffness. And higher stiffness wood is desired for structural products, which is not really surprising. If we build a house out of wood and we put something heavy on the second floor like a bed, we wouldn't want that weight to deform the wood underneath it. However, again, lower stiffness wood can be desirable in certain products. And for an example, I've put up highway materials like signage and guardrails. So we would actually want the wood to flex a little bit in the event of a car collision so that it doesn't transfer the entire force back to that car. So generally when I talk about wood of high quality, I mean high density and high stiffness wood. However, if we know more about the wood we're working with, we can find appropriate products, even if it's not high density and high stiffness, that can maximize that value. So one of the challenging things about studying wood properties and wood quality is they're tremendously variable across multiple scales. And so this slide I'll kind of use as a framework for the rest of the presentation, but I want to illustrate the sources of these variabilities. On the left, you see within tree. So we see a huge amount of variability from the pith to the bark, as well as from the stump to the crown within an individual tree. The next level would be among trees. So if we're comparing neighboring trees that are right next to each other even, and we take an average value of wood density or stiffness, we're likely to find differences. And then across a landscape, when we compare different stands across a landscape, we see quite a bit of variability in these properties. So I have a couple slides to give a little bit more detail to these sources. And on this slide, I'll talk about within tree variation. And this results from the structure of trees. So trees grow by laying down sheaths of wood on top of the existing woody structure every year. And so you can see in this simplified image here, it's kind of like these traffic cones stacked on top of each other. And that leads to variation within a tree because young trees have tremendously different needs than old trees as far as both hydraulic transportation for water and also mechanical support. So I use the phrase candulage a lot. And what I mean by candulage is ring number from pith at a fixed height. And so let's zoom in on our example tree here at the stump cookie. In this case, the example tree grew to year 2020, and it attained a max candulage of 5 rings from the pith. If we look higher in the tree, it still grew to the year 2020, but it only grew 3 rings from the pith, and that's because it took 2 years to reach that height. So this variation from pith to bark is really strong, and it gives rise to the concept of juvenile wood versus mature wood, which a lot of you are probably familiar with. Juvenile wood typically being lower quality wood than the mature wood on the outside of the tree. There's also variation with height because the tree crown influences wood quality, and the closer the wood is to that crown, the more generally wood density is reduced. And I'll always talk about height in terms of a fixed cambial age. So I've got these 2 different axes where I look at ring number from pith as well as height above the ground. So when we're comparing trees to each other, as far as a whole tree value for density, there's a lot of different ways you can look at this, but what I'll focus on in this presentation is fast versus slow grown trees, because this has been a rich topic in the literature for the effect that has on wood density. And to illustrate that, there's these 3 blocks here. You can see a slowly grown tree on the left grading into a more fast grown tree. Some of the past literature has concluded that with changes in growth rate, the late wood width remains the same. And so that means faster trees have a reduced late wood proportion and thus lower density. However, there's been probably an equal number of studies that haven't found anything conclusive in that regard. So that gave us a really interesting question to ask because we have so many dense, overstocked, slow-growing stands in the Southwest. Maybe that slow growth has caused these trees to be of higher density. And when we're comparing a more open-grown stand such as this one to a more closed one like this one, do we see differences in the wood density? So the final level is this landscape scale variation. And I included this graphic from Loblolly Pine in the Southeast to show that the authors of this study were able to assess the changes in specific gravity, which you can think of synonymously with density, across a gradient in latitude and longitude, as well as elevation. And they could find the expected wood density values in different areas of the Southeast. In the Southwest, because we have such greater variation in topography, it makes more sense to think about stand level characteristics and these gradients across the landscape. And the one I'm going to focus on in this presentation primarily is the effect that stand level crown ratio has on wood properties, because this is something that's relatively easy to measure, and it's been shown that it has typically has a strong relationship with wood stiffness. And so to assess this at a relatively rapid pace that doesn't require cutting trees down and sampling the material, we can use what's known as acoustic velocity techniques. And you can see in this image here in the lower right, basically what you do is you hammer in probes into a standing tree bole that are about 1 meter apart, and you send an acoustic wave between the 2 of them, and the speed at which that wave travels correlates really strongly with the stiffness. So in this way, you can very rapidly across the landscape assess a large number of trees and get at that landscape level variation. So with that intro out of the way, these are the objectives that I'm going to frame the rest of the talk around. So there's one of them each for each of those levels of variation. And the first one is to model within tree variation of wood density and stiffness in ponderosa pine. The second one is to look at the effect that growth rate has on wood density. So do we see changes in wood density based on the rate at which the tree grew? And the third one is to look at landscape scale variation and see if we can find factors that lead to changes in wood properties across the landscape. And maybe we can measure them easily and gain a better idea of what we expect the wood properties to be. So getting into the methods now, and I'm first going to introduce my field sites. So the first one is Taylor Woods, which some of you might be familiar with. It's really kind of historic research forest located just outside Flagstaff. And what it is a replicated stand density experiment. So there's different levels of stand density that were established and maintained over the last several decades. So the stand itself was naturally regenerated in 1919 and grew freely until 1962 when these GSL treatments were established. So GSL stands for growing stock level. And you can think about that essentially synonymously with stand basal area. So you can see them in metric in square meters per hectare in this box on the left. I've got them in English units on the next slide. But yeah, they were set to these different stand basal area levels, and each was replicated 3 times. So that's a total of 18 plots. So the most recent thinning occurred in 2017. So ever since 1962, approximately every decade, there's been repeat thinnings to maintain these basal area levels. And so in 2017 was the most recent thinning, and so we were able to go in and sample 9 trees from each of the 6 treatment levels. So that's a total of 54 trees. And so you can see here some representative pictures from Taylor Woods. I'm more familiar thinking in English units in terms of basal area. A lot of you may be as well. So it grades from 30 square feet per acre in the more open park-like stand down to 150 square feet per acre in the more closed canopy stand. So Taylor Woods was the controlled experiment part of my study, but I also was interested in characterizing these variations across a really large area of northern Arizona, and I call this the wild portion of my study. But you can see we got up to, on the locator map, we got up to the north rim here, and then it spanned all the way from the Kaibab down to the Apache Sickeries. And these sites down here, I noticed Chris had, his background was Promontory Peak, and that's actually right where these sites were, the Promontory Butte right there, just north of it. So we sampled a broad range in elevation, and most of them were centered around the Flagstaff, roughly the Flagstaff elevation of 2,200 meters. But we did sample from 2,000 meters up to around 2,700 meters in elevation. And we also covered a broad range in ownership. So there's 3 national forests represented. We got a number of sites from the Centennial State Forest, which is right adjacent to NAU. And we got 1 site from Observatory Mesa, which is Flagstaff city land. So in each of these sites, the first step was to conduct an inventory, and we did 3 plots for each site. These were 10th acre circular plots, and they were all centered around a sample tree, as you can see highlighted here, and I'll just find that on the next slide. So 3 plots for 18 sites, and we took tree measurements of all trees greater than 5 inches diameter breast height on these plots. And we took acoustic velocity on all ponderosa pine trees, which was by far the dominant species. Out of the 985, it was roughly 750-ish ponderosa pine trees. And so here you can see what that acoustic velocity tool looks like in real life. So the sample trees are the ones that we actually harvested and brought back to the lab, the wood quality lab at NAU with my advisor, Dr. Dave Audie. We actually sampled these trees, brought them back to the lab. And so the criteria to be a sample tree was that it was greater than 9 inches diameter breast height and that it was free of any major defect. So we always sampled the plot center tree, and they gave us 3 per site. We also sampled an additional 3 for each site that were randomly selected from the inventory list. So we got roughly a total of 6 trees per site. Not every, some sites we had 4 or 5, but in general we got 6 trees per site. So here's the distribution of trees that we sampled in terms of age. So predominantly you can see they're about that 90 to 100 year age range, which is really common for the second growth around here. But we did sample all the way in the 30s up to, on the north end, some of the trees were 160 years old. And I'll take this time to note that typically we were going to lands that were marked for timber sales, and we worked with local foresters to allow us to come in and harvest these trees ahead of the timber sales for our study. We also got a broad range in height, both in terms of canopy base height and total tree height. And you can see that the tallest trees were upwards of almost 30 meters tall. So as I mentioned, we got 54 trees from Taylor Woods and 103 trees from the greater study area. From all of these trees, we collected discs at multiple heights in the stem at 8-foot intervals, as well as at breast height. And these discs, you can see here on this tree, some of the taller trees we got way more than just 5, but these were taken back to the lab and processed for X-ray densitometry, which I'll talk about in the next slide. We also collected short 3-foot logs, which we call bolts, and these were used to process stiffness samples. And we collected a bolt from breast height of all trees, and from a subsample of trees, we got bolts higher in the tree as well. So a huge amount of work went into processing, storing, and dealing with these samples. I won't go into all the steps, but here's just a couple of slides showing the process. We worked with the local mill, AP Lumber in Flagstaff, to cut the sides off of our bolts so that we could further work it on a table saw. So this is a readout of the X-ray densitometry machine that is in the wood quality lab at NAU. And don't get too lost in these numbers. I'll talk about the important ones in a second. But basically the way it works is you feed in a sample that looks like this. And this is kind of the end result of a lot of processing steps. This is ponderosa pine sample, 2 millimeters thick, and it represents the entire profile from the pith to the bark. You scan the sample and you get a couple of numbers, couple of readings. So first of all, the position, which is a really fine scale. So we had it set to a reading every 25 micrometers, so that's 40 per millimeter. At that position, it tells you what the wood density is, and it calculates this by the difference between the source for an X-ray beam and the detector on the other side, and it can calculate the wood density. And it gives you the year, which was often wrong because it's a pretty simple algorithm for this computer. But I did do extensive cross-dating and dendrochronology work to correct all these years and get a high level of confidence in the years that I was assigning to these rings. So the response variables I'm going to talk about in this presentation, there were several more, but I'm going to focus on ring density, which is just the average density value for each ring, and also ring area increment. So to explain this one a little bit further, it's calculated from ring width, but ring width in a normal tree, normal trees grow larger and then they put wood onto an ever increasing cylinder. So the ring width tends to decline with age. But if you use area, it's a more constant value across the length of the tree's life. And so you can extract signals such as climate and other influences on growth a little bit more solidly from ring area increment. So the other kind of product that we produced and tested are these small clear samples. And these measure 1 by 1 by 16 inches. And we followed pretty rigorous ASTM standards to produce and test these. And we got 2 to 7 samples per bolt. So we wanted to get as many as we could to represent that radial profile and see how this changed from the pith to the bark. But we were limited by the size of a lot of these logs, but we always got at least 2. And so we had to test these at a collaborator at the University of Georgia, Dr. Joe Dolan's lab, because we didn't have this machine on campus. You can see it pictured here. What it does is it supports the sample on either end, and then it applies a load down to the center of the sample until the sample breaks. And along the way, it records the load that's applied, as well as the deflection of the sample. And from that, you can calculate stiffness. And you can see in this image here, this is the way that most of them failed, which is in tension along the bottom of the sample. All right, so when I get into the results and discussion part, I'm going to break it down by these 3 objectives. So first, I'll talk about the within tree variation that I observed. So this is within tree stiffness, and I've put an icon in the upper right. If it's not blocked by your video screen, that'll keep it separated whether I'm talking about density or stiffness, because I know that can be confused sometimes. But this is the pattern in wood stiffness according to cambial age or ring number from pith in the trees. And you can see there's a very steep initial increase before it starts to level off in the outer wood or the mature wood, which has more stable values of stiffness. And this is a pretty well-fitting model. The R-squared was 0.8 and pretty low error statistics. And that indicates that the trees generally conform to this pattern. It describes their progression pretty well. One thing I'll note about my samples is compared to other ones, it's a pretty common pattern for stiffness to follow within trees. But in ponderosa pine, it's actually a pretty slow growth rate before it gets to higher outerwood values. And it's probably no surprise to anybody that's worked with ponderosa pine that there's a large proportion of it is juvenile wood. So here's density. And on the previous slide, I was only showing the breast height samples because there wasn't huge changes with height. But with density, I've got it broken down into different heights measured in meter within the tree. And I've removed some of the extra data points just to clean it up a little bit. But you can see the general pattern with density is that there's an initial decrease from the pith until around ring 25 or 30. and then a really steep increase in wood density as we approach the bark. That kind of levels off. The effective height is generally higher in the tree. We see a reduction in wood density, which is pretty much in line with what other studies have found. Usually higher in the tree, ring for ring, we see reduced wood density. But the other thing to note is the curve tends to flatten, meaning there's less of a difference between the juvenile wood and the mature wood as we go up in the tree, which leads to overall greater uniformity within the trunk. So this was actually a pretty poor fitting model, especially compared to stiffness. The R-squared value is much lower. And what that indicates is that there's a lot more variation tree to tree than there is with wood stiffness. So they don't all necessarily conform to the same pattern. So what can that tell us about using different parts of the tree for different products? This graphic I prepared to kind of break down an example, the bottom two logs of a ponderosa pine tree in terms of what the wood quality we expect to find is in the different parts. And so to start with the mature wood, which is in red, this is the highest density, the highest stiffness wood. If we're going to be producing structural products, it's likely going to come from this zone. As we go more into the juvenile, the core wood in blue, higher on the bowl, it's low density, low stiffness, but in general, there's better uniformity than lower down. There's less changes from pith to bark, which makes processing easier. And then as we go to the bottom core wood, the bottom juvenile wood, which is the largest log of the tree, but unfortunately tends to be the lowest quality wood. We've got low density, low stiffness, and really rapid changes from pith to bark that will result in poor structural performance and a lot of warping when it dries. So to compare these numbers with some other species, I picked out a couple of commercially important Western conifers into this table. And I'm using the mature wood values from my trees to make these comparisons. I pulled these numbers from the Wood Handbook, which is a really commonly used reference for these kind of numbers. So you can see that ponderosa pine, when it comes to stiffness, it's kind of right in the middle. Engelmann and lodgepole are used to produce in some structural applications such as studs. And so ponderosa pine is kind of right in the middle in regards to stiffness. Density, it's actually quite a bit higher than the other ones. And so what that tells me is that the limiting factor to utilizing this wood in structural applications is not necessarily the intrinsic wood properties. There are a lot of issues with the prevalence of knots as well as the stem form and the taper. But if you can find mature clear wood, then it should be of high enough properties to be used in structural applications. All right, so moving on now to the effect that growth rate has. So the way I address this, and I'll just focus on two responses here. There's several more, but I'm just kind of going to highlight these two. I built these models to use two variables as responses, and then as predictors, I use growing stock level, which again is essentially the same as stand basal area, and then several other covariates just to account for variability. And so the question I was asking is that GSL term statistically significant? And in other words, was there an effect of stand basal area on these responses? And to make a long story short, GSL was not a statistically significant predictor of wood density in any of the models I looked at. And to graphically illustrate that, first let's look at ring area increment. And so we would expect this to be driven by changes in stand basal area. It would be surprising if it wasn't. And what we see in this graph are the different colors represent different GSL levels, different stand basal area levels. And you can see from 1960 when the experiment started to about 2020, there's quite a clear separation between these basal area levels in terms of the width of the rings, the area of the rings, which is no surprise. The main reason I included this graph was to provide a counterpoint. When you look at ring density, there really is no patterns that emerge. So with the highest GSL level, we do see the highest ring density, but then the next highest ring density is the lowest GSL level. So that illustrates that there's really no effect of growth rate on wood density at the ring level. And to drill into this one a little bit more, what these results suggest is that there's no ring for ring difference between trees with different growth rates. So let's look at two example trees here. This one on the left, kind of more of an open park-like tree that grew relatively fast and then slowed down. This one on the right grew really slowly in a suppressed stand, and then it was released through maybe management or a fire or something like that. What my results suggest are that if we pick out a single ring like ring 13 from these two trees, we can expect them to have relatively similar wood density. However, this difference between juvenile wood and mature wood still matters, and juvenile wood tends to be lower density than the mature wood. So if we look at this tree on the left, it's got a significantly larger proportion of juvenile wood than the tree on the right. So at the tree level, we're likely to find that this tree produced much poorer quality wood than the tree on the right. And I think this is an interesting comparison to make, because if we think about stands in the future that we're thinning right now, they're going to look more like this tree on the right. They'll be older than 15 years, but they'll have a slow growing core, and then they'll grow a lot faster when they're in the mature wood zone. So moving on to the final level, the landscape scale variation. The way I addressed this was to look at this acoustic velocity, which again is a surrogate for wood stiffness, as a response to crown ratio at the stand level. And so you can see a really strong trend where higher crown ratio was associated with lower stiffness. So the larger the crown was as a proportion of the length of the bowl, the lower the stiffness of the wood that was produced. And this can be useful because it's relatively easy to get information about crown ratio, canopy base height, and that can potentially in the future be used to segregate stands by wood stiffness. And so this is Flagstaff here. This is spatial data from the forestry. It's got tons of attributes in all of these different plots about stand level attributes. I think in the future we could potentially include wood quality attributes that are predicted from stand inventory stuff, and that'll give us a better idea at the planning stages of a project about what kind of wood, what kind of products we could be producing from these trees. And one really easy way to do that is with LiDAR acquisition. I mean, not easy, but relatively good coverage now across almost the entire forestry footprint of LiDAR acquisitions. And you can get information on tree height as well as canopy base height, and you can calculate crown ratio and then have a good idea of what the expected wood stiffness will be. That would require a little bit a larger sample size than I had in my study and a little bit more validation on the ground. But my results suggest that that is a feasible approach to take in the future. So to conclude, I have a slide here on management implications just to kind of wrap everything up. So in ponderosa pine and in my study, the intrinsic wood properties compared favorably with other commercially important species. So it's limited more by stem form and by prevalence of knots, but the wood properties themselves are pretty comparable. If we can segment the trees and produce different products from different parts of a tree, we could potentially achieve greater value. This is operationally really hard to do because we're turning a round thing into several square things, and it just prevents a lot of challenges in maximizing the value, but it could potentially be helped out by forest business clusters where we have different businesses that produce divergent products that are all located close to one another. Thinning is unlikely to have an adverse effect on wood density. Some of the old literature would suggest that these trees that were thinning may start producing poorer quality wood, but my results suggest that the opposite might actually be true because we're increasing the proportion of mature wood in these trees. And finally, we can potentially use inventory data to effectively segregate stands and gain an idea about what the expected wood quality is at the planning stages of these projects. So I have a ton of folks to thank to kind of wrap this up. I won't read through this entire list, but I'll highlight my advisor, Dave Audie in the Wood Quality Lab, who is just a tremendous help throughout this entire project, and my committee members and co-authors. You can probably, if you know any of these people, you can probably see their influence on a lot of this work. So at this time, I'll take questions. There's a fact sheet that the ERI recently published that you should be able to find pretty easily with this title. And there's more links to some of the papers that have been published within this fact sheet. And I'm happy to have a conversation now, and also my email's right here if anybody wants to get in touch in the future. So thanks, everyone. And I'll stop screen sharing for now.
That was really super interesting, Damon. I don't know why that always rings when it's a landline. I have something old fashioned. Oh, and we have a train that goes crazy when it rings too. So woo-hoo. Anyway, sorry. I love that, and I do want to make a mention that I want everybody definitely ask Damon questions. I thought this was, and you laid it out so clearly, like, for people that aren't into that realm of forestry. And so thank you for that. And I do want to make a mention to our partners and a lot of people that aren't here today because of the wildfires in California and Oregon and Washington. I was thinking about them a little bit because we usually have more folks on the call, and I'm sure that's why. So my thoughts are out with our partners in those Western states. But want to open it up for questions. I thought it was absolutely fascinating, and you like I said earlier, it was so understandable, and it's not my field, but and it really also, I think, is encouraging that we can do something with this pine if we become a little bit more innovative maybe as well. So it'd be interesting to see what you all think and your questions. And
did you
and
already all know all that? Because I know I didn't.
Mhm. Yeah, I thought it was fascinating. We'll post the fact sheet as well
Okay.
on the Wood COP call space. I made a note, so I will definitely do that.
Yeah, I can send that to you after the meeting.
Great. Well, go ahead, gang, and especially you sort of want to hear from Jay, because Jay,
Oh, I got lots of questions.
I figured, I was waiting. I was like, Jay's, and with Jay's background and experience in forest industry, it'd be interesting to see what you have to say.
Well, that was a great presentation. I loved it.
Yeah.
I was eating it up, just you were going fast, which I knew you had to. And I was just like, wait, he needs to slow down. I need to ask questions each slide here.
Yeah, I can pull them back
but
up if you want me to.
The slide that really caught my eye was the one where you showed the tree and the wood on the outside, which we all know is the best wood. But then I was really surprised to see that the base, the bottom of the bowl, the inside wood was actually less quality, less dense, or less, I guess, quality more than the upper section. And did you have any reasoning, or did you figure out why that was like that? Yeah, there you go. Why that blue section, the upper juvenile wood, is actually better in uniformity than the lower?
Yeah, so one of the I think one of the explanations for that is the microfibril angle of the wood, which is the cells that make up the wood are composed of microfibrils that are oriented at an angle that's generally not straight. And generally what past research has found is that microfibril angle tends to straighten out as you go higher in the bowl. And the reasons for that I don't think are as clear, but that's something that's been commonly observed in a lot of studies. And I think that explains why stiffness increases with height in tree. Density actually decreased with height in tree, but the wood density of these trees is actually not particularly low. So that's not a huge consequence for the density to increase with the height. Another thing that I saw was that the uniformity across the radial profile from the pith to the bark tended to increase with height in tree, which is really desirable for processing, because that variation from the pith to the bark really leads to a lot of the warping that you see with ponderosa pine. So if there's less of that radial profile variation, then there's less warping.
Okay, did you have, what I've seen through just the years of logging here is that, especially on the Kaibab and other places, that we have a lot of swelled butt, it might be 16 inches butt diameter and 11 inches I've had even DBH. And does that tend to play any kind of role in quality or density or any of the factors you were looking at to see that much of a taper?
It certainly would play a role in the like the milling of it, because it would reduce the small in diameter quite a bit relative to what the butt log diameter is. I think that extreme taper, if you have a 16-inch at the stump and then 11 inches at breast height, you would likely see quite a bit of variation with height, which could lead to issues with warping down on that part of the bowl, so it would influence it. So yeah, I think that would have a strong influence on the properties. The straighter tapered trees would tend to have more uniform properties with height, which is desirable.
Okay.
Would that likely be, sometimes you see like an intense taper down low or something that then kind of reflects a little bit what your graph actually showed, where maybe as you get into that higher wood, you're not having as much of that impact.
That angle, yeah.
Yeah, and I'll qualify that with the second log, often is not of a sufficient size in these trees to even be usable. So if it's a larger tree where it is usable, then the wood quality could be better up there. But I know that a lot of these trees taper so extremely that you can't get a second log out of them.
Did you look at or have I know we dealt with, like, when we got into some areas where we cut bigger trees, 20 plus inches, when they were doing some meadow restoration work and stuff, that the limb knots were so big that even though you're cutting a big tree, the quality was actually worse than some of the smaller trees because your limb knots were 5 to 6, 7 inches, and the board would fall apart because the limb knot.
Yeah.
Did you guys run into some of that with the size of trees you were doing?
Yeah, the meadow trees are definitely going to be lower quality because they've grown really quickly in the beginning. So they've got a large juvenile core and they've got a lot of knots. So I would say my results are more relevant to tree age than tree size, which there's a pretty poor correlation with these trees. So it's really driven by the tree age, these patterns of variation. And so if you have older trees that are beyond that 50-year mark, then that wood outside of 50 years tends to be of a better quality. But in one of those meadow restoration trees, that 50-year zone is going to be huge, and that's going to make up the bulk of the wood.
Last comment. So what I heard you say at the very end, do you think that if we're looking at wood utilization properties and things right now, that this first kind of, well, it'll be the second entry probably, but this entry that we're doing now with the first phase of thinning these forests, you're saying that, we could actually improve the wood for the next time. Does that mean we need to look at different products for this first phase going in because the wood's not going to be as good? And then 50 years from now, when we're maybe re-entering, or even 30, 40 years from now, when we re-enter, the wood's going to be a better quality because you've done that. You've actually improved the wood quality through releasing that tree. Do you see that we might need to be focusing on two different types of wood products? Maybe a lower quality wood product, pallet wood, biomass now, and later we may be able to focus more on structural lumber or CLT or other products that have a little bit more higher value.
I do think that would be an implication that in the future we might be able to produce higher value products because of this management pattern, and not just with that release effect, but if we're running prescribed fires through the forest, it will raise the crown base height, and that can also lead to increases in wood stiffness. So yeah, I don't know if that means, I don't know if it's too early to start planning for that right now, but I think it's something to think about in the distant horizon. That the results suggest that we would have maybe a better chance of producing higher value products, structural salad sawn products in the future.
So Damon, I did a study on the White Mountain Stewardship Project, and I talked to a lot of folks in the White Mountains that had businesses that utilized the small diameter wood, and one of them, and I think it's Randy Timber. Do you remember, Jay? Anyway, they were trying to make guardrail posts for the entire state of Arizona, which I think would be a great way to utilize a lot of our wood. Yeah. And there were certain, maybe you know something about this, and there were certain, and I can look back at my notes, but there were certain requirements that they couldn't meet, at least from whatever supply was available then. And at that time too, supply was an issue. I don't think it's as much as an issue because we didn't have the NEPA done. There were a lot of issues back then, during the White Mountain Stew. And so I'm just wondering if this is something that should be revisited, especially based on your research. You know so much more now. I think FPL was trying to assist this company. I mean, it got to the point where the governor went there for a ribbon cutting ceremony because they really thought this was going to happen. And it's just something that I thought of, and it would be a great use, I think, of potentially using ponderosa pine for, something in our state, our own resources. So it's just something I want to bring up, and potentially we can explore, at a later date.
Yeah. Do you have any documents that came out of that, like any of the studies that they did? I'd be really curious to see that.
Yeah, I'll have to sort of go back into my notes and revisit that. But this was a big deal. And it was really, for me, I felt really hopeful when I heard about this. I was like, wow, this is so incredible. But then they reached these barriers that they couldn't overcome. And it was like, what they were, at least the folks that I interviewed were telling me is that, you know, they're going up to Canada and buying wood rather than using the wood that we have here. And so to me, that was super hopeful. So yes, let me go back and I want to send you some information on that. And if anything, if we don't have a lot of details, we could contact FPL because I know they were working with them for a while. It was
Yeah.
was it Randy Wilson from Timber? Oh, he's in not Nutrioso. Let's see, what's next to Nutrioso? The town.
Alpine? I'm not that familiar with that area.
Yeah.
Yeah, I don't know if they were, but anyway, I'll look that up and I'd love to
Yeah.
send that to you because maybe it's something we can pursue now because there's so much more that's been done.
Mhm.
And I believe there was some kind of regulation that it had to be a certain size, and that's what, you know, befoiled the project basically.
Yeah, I know with those highway materials, you have to do testing. You know, the DOT has to approve it and everything. And I've seen some of those studies, and they'll actually like test crash cars into these guardrails that are made. So I think it's really difficult to have a sample size that's large enough and a study that's big enough to actually like get through those tests. But it would
Right.
be a really good avenue if it could be done. And yeah, it would. A lot of that would depend on the reason why it wasn't successful in the past. I'd be really curious to see that because that would, you know, help decide whether it was a good thing to re-pursue or if whatever they came across then is kind of makes it not possible.
Yeah, it had something to do with the size, and then you needed a specific tree, you know, diameter breast height to meet that size. And at the time, like I said, there were also supply issues at the time. So I will get you that information because I think it's something to look into.
Yeah, I think that'd be a great use.
Okay.
We probably have time for like one more, but Damon, I want to make sure that I get your email right. So maybe pop that in the chat. And
Yeah.
then, of course, people, I think all of you are in the wood utilization space, so you can reach each other there and share resources too, because probably if you share one, everybody would like to see it. And you can drop those fact sheets in there. So feel free to use that space to share information. And then one more, I know there's lots of questions, but who else?
Yeah, I actually sent that to just you, Becca, but I'll do the whole group.
Yeah. Chris or Annie?
Well, thank you very much. I enjoyed the presentation.
Thanks.
Yeah,
That's
my head's just like a dryer. I'm like, oh, so many more things I gotta research and look
Yeah.
up. Like,
Yeah, and we'll definitely get this posted as a recording for those who couldn't make it today. I just wanted to bring up a couple of things. One is